Welcome to Tomorrow Unveiled, the deep dive that unpacks the future, one set of sources at a time. Okay, let's unpack this. If you wanted to know the exact week the rise of the machines stopped being a metaphor and became a manufacturing reality, our dedicated research team suggests it was this week, December 15th through 22nd, 2025.
That really is the profound consensus emerging from all the sources we synthesized. The shift is just, it's unmistakable.
It really is.
And our mission here on Tomorrow Unveiled is to take a hard look at the verified developments from this one single pivotal 7-day period.
Right, we're not interested in the promises or the vapyware.
Exactly. We are focusing entirely on commercialization, on these unprecedented machine learning breakthroughs and the global industrial strategies that immediately moved into deployment.
It's like this period showed a critical, sudden convergence. It wasn't incremental at all.
Not at all. Machines became drastically cheaper, exponentially smarter, and they finally started shipping, moving out of the lab.
And onto the factory floor, into logistics networks, globally. I found myself going through the sheer volume of data our research team compiled, and it was so clear this wasn't just another busy week in tech reporting.
No, it was an undisputed inflection point.
The overwhelming consensus across all those sources is that the robotics industry just crossed a critical threshold. It moved aggressively from, the realm of expensive, temperamental research prototypes.
Which is what defined the entire previous decade, really.
Totally. And it moved to wide-scale, seriously funded commercial integration. These systems are mature enough to actually earn money now.
Precisely. We can definitively state that the whole conversation has shifted.
So we're no longer talking about if robots will arrive.
No. We're talking about how many and how fast they'll be deployed. The implication here is just enormous.
It means the focus has moved.
It's moved from the theoretical capability of a single, beautifully engineered piece of hardware to the real-world operational implications of entire deployed robotic fleets.
Yeah.
And this transformation is driven almost entirely by economics.
And that's where we have to start. So the first area of concrete evidence we really have to explore is this immediate commercial threshold that was crossed. This is the moment where robots stop being like a capital expense for research.
And become a demonstrable industrial asset. Yes.
And our research team confirms a massive cross-corroborated announcement that just sets the stage for everything else. Tesla officially moved its Optimus humanoid robot from the prototype stage
to the mass production phase.
Mass production.
And this pivot to mass production by, let's be clear, an automotive giant is arguably the single most disruptive announcement of the week, maybe even the year.
And it all boils down to one number, doesn't it?
It all boils down to one staggering number,
Yeah.
the projected price point of $20,000 to $30,000 per unit.
I think we have to pause there. We just have to stop on that number because it fundamentally changes the established math for virtually every manufacturing firm, every logistics operation.
And eventually every household on the planet. This is not incremental change.
Not even close.
It's the foundation of the revolution. Our analysis here on Tomorrow Unveiled always involves looking at the competing metrics, right? So let's compare that price. Let's just say we anchor it at $25,000.
Okay.
To the fully loaded cost of human labor. In major manufacturing hubs across North America, Europe, Asia, the annual cost of a human worker, when you factor in wages, Social Security, health insurance, paid time off, training,
All of it.
It often exceeds $50,000, even $60,000 annually.
And crucially, that's for a single shift. That's just for 8 hours a day, 5 days a week.
Right. The machine is not limited in the same way.
Not at all.
So when you introduce a machine that costs $25,000 up front, which is a one-time capital expense, and that machine can operate for 2 or even 3 shifts for multiple years with only minor maintenance and energy costs.
The entire return on investment, the ROI, it shifts from being sort of a risky incremental improvement to
being truly exponential and immediate. The payback period just collapses to a matter of months.
And this economic reality, it underpins every single deployment strategy we're going to talk about.
It's the whole story.
That economic analysis makes perfect sense. But, okay, here's where the critical friction comes in for me. Why can Tesla achieve this price floor?
Right.
I mean, you have competitors like Figure and 1X. These are sophisticated engineering firms, and they're still estimating the cost for their units to be well over $100,000 right now.
So what allows this massive disruption?
Yeah, what's the secret?
It's the central question.
Yeah.
And the answer is all about supply chain synergies. It's a strategy that only an established, high-volume automotive manufacturer is uniquely positioned to execute right now.
Okay.
The research team highlights a critical concept here. Optimus is being built as a car in the shape of a human.
A car in the shape of a human.
They are leveraging components that they already mass-produce for their electric vehicles.
So you mean things like the battery cells, certain control mechanisms, that kind of thing?
Precisely. The sophisticated actuators that control movement, the battery cells for power, and maybe most importantly, the FSD, the full self-driving inference computer, they're all derived directly from the Model 3 and Model Y supply chains.
And when you're producing these complex components at the scale of millions of vehicles a year,
the cost of that marginal component for the robot just drops dramatically. This established manufacturing leverage is what lets them dictate the pricing floor for the entire, nascent humanoid industry.
Let's elaborate on that FSD inference computer. For listeners who might not be deep into Tesla's architecture, what exactly is an inference computer, and why is it so essential for the robot?
That's a great distinction to make. In the AI world, you have training and you have inference. Training is the intensive months-long process of teaching the neural network a skill.
Right.
Inference is the act of using that learned skill in real time. So the FSD inference computer is the high-speed brain that takes the robot's visual input and its learned model, for example, how to pick up a box, and it executes those complex motor commands instantly.
So by using an existing mass-produced computer that was developed for navigating roads, they can just plug a brain into Optimus.
A high-power, low-cost brain capable of making split-second complex decisions in a factory. Their competitors have to design, test, and source these specialized chips from scratch at really low volumes.
Which is why their costs just balloon.
Exactly.
So their strategy is just vertical integration taken to its logical extreme. They're not just announcing production for sale, they're announcing this massive internal deployment.
Right, which seems to be the second critical pillar of their strategic advantage.
It is.
Absolutely.
Yeah.
The internal deployment strategy is, from a data acquisition perspective, it's brilliant.
How so?
Tesla is embedding Optimus units immediately into its own gigafactories. They're targeting these high-volume, repetitive areas like the battery cell production lines.
Which creates what the sources are calling a massive, closed-loop, adversarial training network.
Think of it this way. Every hour, an Optimus spends moving battery cells, or maybe struggling with a dropped component or perfecting a grip. That labor cost is being converted directly into a proprietary data asset for training their neural networks.
So their learning curve. All those inevitable moments of failure and confusion and adaptation that every robot has at the beginning is absorbed internally.
Yes. And it's generating unique, high-value data that no competitor can possibly access. They're essentially getting paid in proprietary operational data.
Wow.
That is precisely the flywheel effect they've engineered. They absorb the inevitable production hell that comes with scaling new hardware internally.
And that shields the brand from the public failures that often derail competitors who have to rely on external pilot programs.
The more robots they deploy, the smarter their centralized AI gets. The smarter the AI gets, the more tasks the robot can perform, which in turn justifies more internal production.
It's a self-reinforcing, vertically integrated system for both hardware scaling and intelligence acquisition.
Perfectly put.
So that summarizes the Western model perfectly. You bet everything on the sophistication and scale of the software intelligence, and the hardware economies will follow from your own internal adoption.
Right.
But our sources show the Asian sector, particularly China and South Korea, demonstrated a starkly different but equally powerful strategy this week. They're focusing on immediate, tangible deployment speed, a hardware-first industrial approach.
The contrast is truly illustrative of the geopolitical bifurcation we see in this sector. It's fascinating.
Oh, so?
While the West was announcing manufacturing intent and projected future pricing, the promise of scale, the Asian manufacturers demonstrated immediate delivery and tangible scale.
And UBTech Robotics' announcement was a definitive milestone there. Some sources even called it the day one of the industrial humanoid era.
Because they began mass delivery of their Walker S2 robots.
And this wasn't some PR stunt with a couple of demo units showing up at a client's lab, was it?
Not at all. We are talking about genuine industrial scale deployment. Unlike those pilot programs of 1 or 2 units we saw throughout 2024, the UBTech deployment involves hundreds of units and confirmed commercial orders exceeding 800 million Chinese yuan.
Which translates to approximately, what, 112 million US dollars?
$112 million. This volume shifts the technology out of the experimental research budget line for their customers and firmly into the standard capital expenditure budget.
So when companies are committing that kind of money to fleets, they're not experimenting anymore.
No, they are betting on immediate, measurable ROI.
It sounds like the design itself had to be optimized entirely for that industrial goal, right? What specific engineering feature really shows that focus?
It does. The Walker S2 is not some general-purpose concept machine. It is specifically engineered for the 247 reality of the factory floor.
Okay.
And the most important feature, the one that indicates a deep understanding of industrial KPIs, is its battery swapping capability.
Why is that battery swap so crucial in an industrial context?
Because in a high-volume, continuous manufacturing environment, a 3-shift cycle running 24/7 downtime is a massive bottleneck.
Right. If a robot has to plug into a wall and charge for 4 hours, it's immediately less productive than a human.
Who can be replaced in a shift change?
Yeah.
Exactly. But a robot that can swap its power source in 2 minutes.
It's a seamless drop-in 3-shift replacement for a human worker.
UB Tech solved the efficiency metric before they solved the generalized intelligence problem. They prioritize throughput over ultimate sophistication.
That's a phenomenal design choice. And moving from efficiency to safety, the CATL case study from this week is equally fascinating. It goes beyond simple labor replacement and moves into these critical, high-risk tasks.
Tasks that humans really shouldn't be doing in the first place.
Exactly.
The deployment of the Moz robot, often called Xiaomo by the battery giant CATL, the world's largest EV battery manufacturer, it provides immediate and irrefutable justification for automation entirely on safety grounds.
And these robots are doing what, exactly?
They're performing high-risk, precision tasks like connecting high-voltage test plugs on the battery assembly line.
Which is inherently dangerous for people. You've got the extreme risk of electrocution, especially when you're moving massive amounts of power.
Exactly. The human element introduces the risk of fatigue, of error, of catastrophic injury.
And the data CATL released is pretty compelling.
It's validated and compelling. These robots are achieving a confirmed 99% success rate in these precise, dangerous maneuvers.
So this deployment gives an immediate economic justification by improving quality control.
But the primary return is in safety metrics and liability reduction. Humanoids aren't just doing tedious tasks in 2025. They're performing tasks too dangerous for people, demonstrating immediate, tangible value that creates a commercially valuable beachhead.
It's a clear signal that robotics maturity has crossed the safety threshold. The scale and commercial readiness we just discussed, the $20,000 price point, the $100 million fleet deployments, the 99% accuracy on high-risk tasks, none of that would be possible without a simultaneous, explosive revolution in how these machines learn.
Right. We need to shift our focus now to the scientific breakthroughs that made these mass deployments viable.
It's truly fascinating, the interconnectedness here.
It is. The physical barriers that prevented mass deployment have fallen precisely because the cognitive barriers, the challenges of teaching a machine to adapt and generalize, have been aggressively lowered.
And the critical consensus across our source material points to a monumental advance in data efficiency and generalized learning.
It does.
And the single most consequential technical advance of the week, according to the analysis from our dedicated research team, came from a paper detailing a massive leap in learning efficiency. Let's spend some time defining the MT3 method.
MT3, multitask trajectory transfer. This breakthrough, which the research team analyzed, it fundamentally changes the economics of training.
Okay.
If the hardware cost bottleneck was $100,000 per robot, the training cost bottleneck was hundreds of human hours just to get a machine to perform one new factory function.
Okay, so let's unpack this with some clarity.
Okay.
What was the old problem that MT3 effectively solved?
The old problem was severe data thirst and lack of generalization, and it was primarily solved with something called behavioral cloning.
Right.
To teach an industrial robot like the Sawyer arm a new task, say sorting 10 different components on a conveyor belt, you traditionally needed hundreds, sometimes thousands, of human demonstrations of that exact task in that exact environment.
Which was painfully slow, immensely expensive, and critically brittle.
Very brittle. If the components or the lighting changed even slightly, the robot would often fail and have to be completely retrained.
So if you spent a month teaching it to fold a white t-shirt on a dark wooden table, it would completely fail if you gave it a blue polo shirt and put it on a white metal counter.
Exactly. It was too literal. It was confined to the exact data it was trained on.
So what does MT3 do differently?
The MT3 method solved this crippling inefficiency bottleneck through a sophisticated technique called trajectory decomposition.
Trajectory decomposition.
The core innovation here is structural. The system breaks every physical movement the robot performs into two distinct separate phases: alignment and interaction.
Explain those two phases for the listener.
Alignment is the high-level generalized phase. It's the movement required to get the arm or the hand or the end effector into the right starting position near the object of interest.
In interaction.
Interaction is the low-level specific phase, the actual work being done. Gripping the object, pushing a button, applying force.
So by separating the where to go from the what to do?
Yes, that separation is the genius of it. It allows the robot to immediately retrieve and generalize similar alignments from a massive pre-existing library of past experiences, even if those past experiences were related to totally different tasks.
Can you give an example?
Sure. If the robot has learned the alignment trajectory to reach for an object on a high shelf for task A, say, retrieval,
Okay.
it can instantly apply that exact same alignment trajectory to a completely new task B, like flipping a switch on that same high shelf.
And it does that using only a single human demonstration for the new interaction phase.
Exactly. One demonstration.
That is the crucial metric then. 1,000 tasks in one day. That number is the definitive, documented end of the special-purpose robot era that dominated industrial automation for decades.
It truly is. This few-shot learning capability means that a general-purpose robot, whether it's Optimus, Walker, or Digit, can be unboxed in a brand new factory or even a home and learn the layout, the tooling, the specific chores of that environment in a single afternoon.
By adapting its existing knowledge base.
Yes, and this unprecedented leap in efficiency is what makes the mass commercialization and the $20,000 price point we talked about economically viable. The hardware is cheap enough.
And the software is finally smart enough to learn on the fly.
Mm-hmm.
And this new efficiency, it relies heavily on advanced, large-scale AI models that link that perception and rapid learning directly to complex action. This brings us to the concept of vision, language, and action models, VLAs.
What's fascinating here is how the intelligence engine is leveraging human knowledge on a massive scale. We're seeing the powerful emergence of VLA models like Microsoft's VIGRA VLA and the X-Humanoid pipeline.
And these systems are being trained on what?
Millions of hours of real-world human video, text descriptions, and corresponding motor data. Their purpose is to bridge the massive gap between high-level human intent and the low-level motor control necessary for physical movement.
So instead of a human engineer writing millions of lines of machine code, the operator can just use natural language, just speak to it.
Exactly. This fundamentally solves the reprogrammability bottleneck, which was one of the single greatest sources of friction and cost in legacy robotics.
I mean, historically, if the workflow changed, you needed weeks of engineering time.
Weeks. Now, instead of coding millions of precise coordinates, an operator can give a high-level, human-readable instruction. Something like, move those blue pallets to the shipping dock and stack them 3 high.
And the VLA neural network interprets that intent.
It breaks it down into a sequence of complex motor actions, determines the optimal path, calculates the necessary grip force based on the perceived weight and material, and then executes the entire seamless maneuver.
So changing a complex factory job that used to take human engineers weeks of reprogramming and calibration now just requires a single accurate sentence from a floor manager.
That's a staggering improvement in flexibility.
It's the paradigm shift that unlocks mass adoption.
It is. It means the robot is no longer a rigid, scripted tool capable of only one thing. It's a flexible, intelligent agent that can adapt instantly to a changing inventory or a new layout based on natural human language input.
The software is finally catching up to the sophisticated physical capabilities of the hardware.
And the combination of MT3's rapid learning and VLA's flexible control is the technical foundation of this revolution.
The movement this week was clearly not just technological, it was heavily financial. The sources confirm that the industry is moving rapidly beyond early-stage venture capital bets.
And into sophisticated financial structuring and massive capital integration, these robotic systems are becoming tangible liquid assets.
They absolutely are. And the strategic deal between 1X Technologies, a cutting-edge humanoid company, and the private equity firm EQT is, it's arguably the most sophisticated financial arrangement in the history of the sector.
It marks the robot as a truly liquid, deployable financial instrument.
And EQT is not a small player. They are one of the world's largest private equity firms, managing, 267 billion euros in assets.
Right.
So what exactly does this partnership entail, and why is EQT making this enormous commitment?
The deal involves the strategic deployment of up to 10 10,000 NEO robots
10,000.
across EQT's massive and diverse portfolio of companies between 2026 and 2030. These companies span logistics, healthcare, manufacturing, industrial services, all firms that EQT already owns or manages.
That is the key insight, isn't it? EQT isn't just investing in 1X, they're creating an internal captive market for the robot.
Yes, they aren't waiting for the market to slowly demand robots. They are effectively mandating the adoption internally across hundreds of existing businesses
So this arrangement transforms the robot from a product that 1X has to go out and sell.
into a standardized financial instrument for EQT. Their strategy is elegantly simple. Deploy the robotic assets to dramatically improve the operational margins and efficiency of their portfolio companies.
So by lowering labor costs, increasing throughput, and extending operational hours, they increase the overall valuation and profitability of that entire portfolio.
This is asset optimization at a massive, sophisticated financial scale. It confirms that private equity now views robotics as a standard lever for modernization, not just some risky technology bet.
That is a phenomenal insight into how institutional finance is viewing embodied AI, and it solves the sales friction problem.
Completely. 1X doesn't have to convince thousands of independent CEOs. EQT provides a massive guaranteed order book and mandates the adoption from the top down.
It just accelerates deployment dramatically.
And it validates the pivot of many robot makers, from the uncertain, expensive consumer dream like the robot butler to the immediate, controlled profitability of industrial reality. The warehouse, the logistics center, the hospital.
If you're finding this insightful, please take a moment to like this video, subscribe to Tomorrow Unveiled, and consider hitting that new hype button to help us reach more viewers. And of course, be sure to turn on notifications so you never miss an update on the future. We touched on the diverging strategies of the East and West earlier. If we connect this EQT financial structure and the Tesla internal deployment to the bigger picture, we see a clear geopolitical bifurcation in strategy emerging from the events of this week.
This divergence is becoming starkly defined. The sources suggest the Chinese market, supported by strong state initiatives and leveraging their, unparalleled manufacturing capability, prioritizes rapid scaling, low hardware cost, and immediate volumetric deployment.
And Unitree reinforced this with reports targeting a staggering $16,000 price point for a consumer-focused humanoid unit,
which significantly undercuts all established Western competitors.
That hyper-aggressive price point, combined with UBTech's demonstrated mass deliveries, it just emphasizes hardware dominance and speed of saturation. They're winning on volume and cost.
While the Western market, led by Tesla, Figure 1X, and Hyundai, is prioritizing sophisticated AI models, premium system integration, and higher-end manufacturing.
Right, and Hyundai Motor Group, the owners of Boston Dynamics, reinforced this Western focus with the pre-announcement of the new Atlas debut.
Planned for CES 2026.
Atlas is famous globally for its jaw-dropping videos of parkour, flips, and its very distinct, somewhat loud, messy hydraulic system.
It is.
What's the commercial significance of this planned new version?
The shift is both technical and strategic. The sources confirm that the new version is transitioning away from that high-powered, high-maintenance hydraulic platform to a cleaner, more commercially scalable electric platform.
And that's a crucial enabler for mass scale.
It is, because it allows them to align Atlas with existing EV supply chains, much like Tesla, leading to lower manufacturing costs, simplified maintenance, and reduced operating noise.
Making it far more palatable for controlled industrial environments.
And this transition isn't just about a single, flashy machine. It sounds like it's being framed within a larger, holistic system strategy for Hyundai.
It is.
Absolutely. Hyundai frames this within its group-wide, software-defined factory, or SDF, strategy. They view Atlas not as a standalone, headline-grabbing machine,
but as an integrated node in a comprehensive software network that manages the entire production environment.
Right. It works alongside their other platforms, like the MobED logistics platforms, creating a tightly controlled, integrated system for managing production lines and logistics flow.
So the West is fundamentally betting on the intelligence network.
And the East is betting on the sheer volume of low-cost units.
Speaking of logistics, we need to talk about reliability, because in a warehouse environment, consistency and reliability, they truly trump speed or flashiness. And a crucial validation happened this week regarding that very metric.
We saw crucial commercial validation of logistics this week with the commercial agreement between Agility Robotics and Mercado Libre, the massive Latin American e-commerce giant.
And they're deploying Digit robots in fulfillment centers in Texas.
They are.
And the key advantage of Digit, which the research team highlights, is its immediate ability to operate in existing human-centric warehouses, the so-called brownfield advantage.
That's the strategic difference. Digit is explicitly designed to navigate standard human aisles, open standard doors, and climb standard stairs,
Environments already built and certified for human use.
which requires no expensive structural overhaul, representing a huge capital expenditure saving for adoption. But the most critical signal of the technology's maturity and industrial reliability
Is that number?
is the confirmed metric of 100,000 totes moved during the trial phase.
Why is achieving that specific metric more important than, say, demonstrating how fast the robot can sprint or how much weight it can carry?
Because in logistics, consistency is king. If your automation solution constantly requires human intervention, it's not automation, it's an expensive distraction. A machine that reliably moves 100,000 totes without a critical failure, consistently operating for long hours, is revolutionary. A robot that is 10% faster but breaks down once a week is an industrial liability.
So this singular focus on long-horizon autonomy and industrial reliability, it validates that these systems are ready to operate 24/7 without friction.
It moves the internal business discussion from can it do the job to how many can we deploy tomorrow.
While humanoids dominate the headlines, and they should, given the financial stakes and the cultural fascination, our research team's findings show parallel, high-impact advances in systems smaller and larger than the human form.
Right. This validates the comprehensive progress across the entire robotics ecosystem.
It isn't just a moment for bipedal robots.
No, the entire universe of autonomous systems is expanding at both the high end and the low end of the scale spectrum simultaneously. It proves the fundamental technologies are maturing everywhere.
Here's where the analysis gets significantly complex. At the complete other end of the size spectrum, researchers achieved a breakthrough that overcomes a 40-year barrier in robotics. We are talking about micro-robotics.
Specifically, the sources detail the creation of programmable autonomous robots smaller than a grain of salt
Smaller than a grain of salt.
by UPenn and UMIC researchers. If you saw the image provided by the research team, it's literally a speck of gray on a human finger. That is a fully autonomous machine with onboard processing.
That immediately raises the core engineering question. How does something that small move? At that extreme microscale, traditional physics, it just doesn't apply, right? You can't fit a functional gear.
That is the exact challenge, the tyranny of the microscale, what is known as the low Reynolds number. At that level, fluid, even water, feels like thick syrup or honey.
Wow.
Inertia is negligible, and viscosity dominates. The researchers solved the propulsion problem brilliantly by using onboard photovoltaic cells to convert light into electrical fields.
So they use light to power their movement by creating a localized electric field around the robot.
Precisely. The electrical field pushes ions in the surrounding viscous fluid, enabling the tiny robot to swim autonomously through the liquid. It's an elegant solution.
It bypasses the need for complex, failure-prone mechanical actuators at that microscale.
It's a complete re-engineering of locomotion based on physics you only encounter when you're smaller than a human hair.
That's incredible. What are the immediate, tangible implications for systems smaller than a grain of salt?
The most immediate and transformative applications are medical and diagnostic. These robots aren't passive particles. They integrate sensors and computing based on CMOS technology.
So they could theoretically be injected into the human body.
Through the bloodstream for targeted drug delivery. Imagine chemotherapy reaching a specific tumor without affecting the rest of the body. They could perform microsurgery or advanced diagnostics from within.
This is the Fantastic Voyage scenario.
Finally becoming technically plausible. It's shifting from science fiction to a clear, near-term engineering pathway for 2026.
That's the invisible revolution happening, while the visible revolution is unfolding on the factory floor. So, now let's look at the infrastructure that supports all autonomous systems, especially those that fly, where sensing and efficiency are paramount.
This week also highlighted significant advancements in sensing infrastructure, critical for logistics, inspection, and defense. Specifically, a partnership supplying solid-state LiDAR for delivery drones revealed new units that are 66% lighter than previous generations.
66% lighter, while offering double the resolution.
Right.
That difference in weight sounds like a massive game for drones, which are so constrained by payload and battery life.
It is absolutely critical. In drone delivery, weight is payload, Every gram saved on the sensor package is either a gram added to the parcel the drone can carry,
Increasing revenue potential.
or a minute added to the flight time, increasing logistical reach. This miniaturization allows delivery drones to see their environment with the fidelity previously only available in autonomous cars.
So it enables them to navigate complex, chaotic urban environments, avoiding thin power lines, sudden tree branches, or moving obstacles.
Safely and efficiently, which is the final major safety barrier to wide-scale delivery deployment.
And finally, let's talk about AI accelerating its own progress. We saw news from Google DeepMind's new Automated Materials Discovery Lab in the UK, which creates a critical virtuous cycle in the research process.
This is what we call the force multiplier, the self-improving loop. AI is now being used to discover better, more efficient battery chemistries, superior catalysts, next-generation superconductors.
And it's not a human running the experiment.
No, it's an automated materials discovery lab where the AI decides the next experiment to run. The virtuous cycle is clear. AI designs better, lighter, more energy-dense materials.
Those materials are used to build better, lighter, more powerful robots.
And those robots gather more high-quality data faster, making the central AI even smarter. This continuous automated loop, often managed by systems called AI co-scientists, has the potential to compress decades of traditional material science research into mere years.
It's accelerating the entire robotics and energy storage industry exponentially.
It's the machines accelerating their own evolution.
Robots aren't just technical and financial assets, they are rapidly becoming cultural figures, which is leading to some fascinating and sometimes unexpected friction points and conversations about human empathy and boundaries.
As these sophisticated systems leave the controlled, sterile environment of the lab and enter public spaces, they inevitably encounter the messy, unpredictable reality of human culture.
And this week provided several compelling case studies on both normalization and friction.
It did.
Unitree, who we identified as a key player in the Chinese market focused on hardware scale, they really mastered the art of normalization through entertainment.
Their strategy was a masterclass in making the unfamiliar familiar and even desirable. They deployed 6 of their G1 robots to perform synchronized dance choreography alongside the pop star Wang Li Home at a major concert event.
And this simple act, it just reframed the robots completely.
It moved them from being perceived as distant industrial tools or, potential existential threats to engaging high-tech entertainers. It's a clever form of public acceptance engineering.
Even industry leaders, including Elon Musk, reacted positively.
Right, highlighting the technical achievement of synchronizing 6 dynamic bipedal robots to music, which requires robust dynamic control and incredibly low latency communication.
But that cultural push toward human likeness, it immediately runs into what the sources are calling the empathy gap, which became highly visible this week with that viral video involving the NBA star Kyrie Irving.
The video, which showed Irving playfully but forcefully shoving a Unitree robot, sparked an immediate and wide-ranging conversation online about robot abuse.
And the key finding from the research team's analysis of the public reaction is this immediate mirror neuron response it evoked in people.
When a robot looks and moves too much like a human, its mistreatment evokes a sense of discomfort or pity, even though the machine is inanimate. We feel bad for the machine because we recognize a version of ourselves in it.
So the uncanny valley isn't solely a visual phenomenon anymore. It's extending into behavioral and emotional responses too.
Exactly. The industry has a difficult tightrope to walk. If robots are too aggressively human-like, their mistreatment becomes taboo, and humans might be hesitant to work alongside them for fear of harming them.
And conversely, if they're too machine-like, humans will treat them as mere appliances.
Which might hinder their smooth integration into social spaces. The Kyrie Irving incident demonstrated that as robots enter our public and leisure spaces, we are already starting the difficult, messy process of determining new social norms and boundaries around them.
And other companies are strategically trying to bridge that gap with personality and semantic understanding to promote acceptance, right?
Figure AI's holiday demo is an excellent example of this tactical approach. They featured the Figure 03 robot successfully wrapping a gift, but the critical detail was the robot making a joke or a wry comment while performing the task.
By programming the robot not just to perform the action, but to interpret and generate humor based on its task.
Figure's trying to gain acceptance in the domestic market through perceived intelligence and friendliness. This semantic understanding relies heavily on those VLA models we discussed earlier.
A machine that can demonstrate self-awareness or make a joke is immediately perceived by the human brain as safer and more intelligent than one that is just silent and rigidly functional.
Exactly.
If you're listening on a podcast service like Apple Podcasts or Spotify, we'd be incredibly grateful if you could leave us a rating and review for Tomorrow Unveiled. It truly helps us reach new listeners. Also, we love hearing your thoughts. Whether you're on YouTube or your favorite podcast app, leave a comment and let us know what you think about the ethical implications of a robot with a sense of humor.
This cultural interface, while complex, leads us directly to the single biggest non-technical challenge identified by the research team for 2026: safety.
Specifically, the rising specter of the kinetic cyber threat.
Yes.
This is a massive issue. As these powerful general-purpose systems scale and are connected to internal factory networks, how do we ensure physical safety when their entire intelligence and motor control is digitally determined?
The critical consensus warning from our research team is sobering. I would say bordering on alarming.
It must be taken seriously.
It has to be. Sources confirm that cybersecurity analysts are issuing strong warnings that the complex, multi-layered software stacks controlling these new robots are currently easier to hack than your standard PC.
Easier to hack than a PC.
And this lack of robust cyber preparation is identified as the industry's major systemic oversight in the rush to achieve scale and deployment speed.
And the implication here is fundamentally different from traditional corporate data breaches, where the harm is financial or informational.
Exactly. A hacked laptop steals data. That leads to financial or reputation loss. That's bad enough.
But a hacked humanoid robot poses a kinetic cyber threat.
It's embodied AI with high torque, industrial-grade force capacity.
Mm-hmm.
A malicious actor who gains control of the robot's operating system could essentially weaponize the machine.
Turning it into a physical agent.
Yes.
Can you give us a concrete example of what a kinetic cyber attack might look like in a factory setting?
Sure. Consider the battery manufacturing floor we discussed earlier. An attacker could exploit a network vulnerability to override the robot's internal safety parameters.
So instead of precisely placing a battery component,
The robot could use as high-torque actuators to physically injure a human coworker, intentionally dismantle high-value equipment like a specialized laser cutter, or simply destroy the integrity of the production line.
this is a form of sabotage with physical consequences. It's not data theft. It's physical violence and industrial disruption.
And the lack of preparation for kinetic security is projected to be a major regulatory and safety challenge in 2026. The complexity of integrating multiple software and hardware layers is creating hidden vulnerabilities.
Vulnerabilities that current industrial security protocols just aren't designed to handle.
We expect a massive acceleration in the development of robotic cyber defense startups attempting to address this urgent physical security gap. The industry's focus must shift rapidly from can the robot work to can the robot be trusted to work safely in a connected environment. Hashtag tag outro.
So what does this all mean for us, the audience of Tomorrow Unveiled? The week of December 15, 2025 truly crystallized the transition into the irreversible deployment era of robotics.
It did. Based on the overwhelming mountain of evidence our dedicated research team compiled, 3 major takeaways define this seismic shift.
And the first is that the technology has achieved commercial reality.
Absolutely. The systems are priced, they are funded by massive private equity deals, and they're deployed at fleet scale. Tesla's ability to set a $20,000 price point, coupled with UBTech's immediate delivery of industrial fleets, has permanently altered the economics of global labor and manufacturing capital expenditure.
Second, the core challenge of learning has been fundamentally solved.
Right. New AI models like the MT3 method have cracked the data inefficiency bottleneck, allowing complex systems to master 1,000 tasks with a single human demonstration.
Which makes the concept of truly general-purpose robots, which can adapt to any new environment quickly, a near-term viable reality.
And third, a clear geopolitical bifurcation is underway. The world is splitting into 2 clear technospheres.
One focused on rapid, state-supported hardware scaling and aggressive cost reduction in the East.
And the other focused on sophisticated, flexible software intelligence and premium systematic integration in the West.
The data is just undeniable. The economic argument against automation on grounds of cost has now collapsed. With the hardware costs potentially dropping below the annual cost of human subsistence, the questions for the next 5 years are no longer technological.
No, they are fundamentally societal and political.
This raises an important question.
Who controls this rapidly growing robotic labor force? And how will global labor laws, social contracts, and tax structures need to adapt to what we might call the labor singularity?
It's a big question.
As efficiency reaches this unprecedented level, the challenge shifts from engineering machines that work to governing a future where human labor is optional, not fundamental, to the global economy. That is something significant for you to mull or explore on your own as the machines continue their undeniable rise.
Thank you for joining us for this look into the future of robotics here on Tomorrow Unveiled. We'll be back next week to unveil what comes next.